Hello everyone! In the previous two add-on videos to Why Algorithms, we discussed Abstract Symbol Table API, which maintains key value pairs. In this video, we will discuss geometrical structure named graph. It's about some entities which may be linked, connected to each other. We will discuss real-life examples and a large set of problems involving graphs very soon. In most cases, you can intuitively understand how real-life examples are mapped to graph structure, but sometimes it requires extra efforts. This video will unleash our imagination even more. Ready? Let's go! There are few graph terms known. We will be focused on graph as a set of vertices connected pairwise by edges. Sometimes directions of moving from one vertex to another is important. We can allow moving in both or just one direction. To successfully use graph-related algorithms, we need to be familiar with graph terminology. Very soon, you'll see how useful to know meaning of certain terms in solving practical tasks. Let's check these terms now. If all edges are bidirectional, such graph considered as undirected graph. In this case, direction of edges are not even marked. If edges of graph have associated directions, such graph named as directed graph or dgraph. And we can mark direction by arrows, having beginning and end. It's easy to see a lot of examples of graphs in real life. For example, we can have car roads with traffic allowed in both directions, as well as just in one direction between intersections. Intersections are our vertices. Such example, like any other examples, can be for simplicity depicted as a related graph. Similar with avia tickets, you can purchase one-way or return tickets. Airports are our vertices here. We can have computer networks packets routing between two endpoints via many routers. Endpoints and routers are our vertices. It might be automated airport baggage system connecting points of accepting baggage and routes till exits to particular airplane. Or robotized mail service to sort postal boxes before delivery. Or a robotized warehouse with lots of goods for storing and further packing for delivery. Graphs might be edge-weighted, which means a number called weight is assigned to each edge. Such weight can represent some meaningful real-life parameters depending on the task. For example, distance between intersections, distance between cities or airports, or maybe avia tickets prices, or maximum possible transport capacity, like max weight or max number of postal boxes per hour on a lane, or number of people daily commuted by train, etc. Path is a sequence of vertices connected by edges. For example, your trip with layovers when you have one or more airports between your initial departure airport and final destination airport. All the way through all airports is the path in this case. For simplicity and better understanding, you can consider path as direct when two vertices directly connected by just one edge, or indirect when there are two or more edges between vertices. Term closely related to path. Two vertices are connected if there is a path between them. Just imagine several cities as graph's vertices. Some of them are built on a mainland and some of them on island. They can be connected by paved roads and bridges, our possible graph's edges. If there are no bridges between island and mainland, we cannot find any city on island being connected to any city on a mainland. But two cities within the same island, for example, could be connected. Even though graph by definition is a set of vertices connected pairwise by edges, we need to realize that there might be two extreme examples of graphs. First, sparse extreme, graph with set of vertices and no or not yet connecting edges. Second, dense extreme, graph with full mesh of edges connecting each vertex to all other vertices. I'm excluding possible potential anomalies like self-loop, edge from and to the same vertex, or parallel edges between the same two vertices. First extreme analogical example is about several cities not yet connected by any paved roads or bridges at all. Second extreme analogical example is about all cities connected to each other directly by paved roads. Real-world graph examples observed to be sparse. Not as extreme, but still sparse. For example, no need to connect each city to each other city by road. Some of cities might be just transit cities, connecting others indirectly. From order of growth runtime algorithm perspective, in general, the more edges in the graph, the more steps of algorithms to be executed. Here is another useful term. Vertex degree is number of edges connected to vertex. This is vertex of degree 3, and this vertex is of degree 2. For sparse graphs, average vertex degree is relatively small, even overall number of vertices may be large. Do you remember term two vertices are connected if there is a path between them? If graph is sparse, not only average vertices degree will be small, but as well not all vertices may be even connected. Therefore, another consequent and useful term here is connected component. Connected component is a maximal set of connected vertices. To clarify, that means any two vertices in connected component are connected, having direct or indirect path between them. Any other vertex in the graph which does not belong to particular connected component is not connected to vertices of this connected component. That consequently means that graph may have more than one connected component. For analogical example, we can have graph with vertices cities built on 3 different islands without any edges bridges between islands. But all cities within each island are connected by edges roads, directly or indirectly. Therefore, we have total 3 connected components in our graph. Why is it convenient to introduce connected component term? Because for our algorithms, for example, it would be easier to find a quick answer: are 2 vertices connected or not? If 2 vertices belong to the same connected component, they are connected. Otherwise, they are not. You can see that within the same island, these 2 vertices are connected, have path between them, indirect though. But these 2 vertices are not connected because they belong to different connected components, since they are on different, not interconnected islands. Next term, cycle. Path, which first and the last vertices are the same, and you are not using any edge twice on the way. Like traveling in a loop, for example, visiting all coast cities on island clockwise, and returning back to the same city, which you started your trip from. Just a comparative component, trees, which we discussed in the previous videos, why algorithms, are one of the examples of graph. But trees cannot have cycles by their definition. They have root node connected to all subtrees, and there are no 2 subtrees directly interconnected on any level. With trees, you don't have 2 or more alternative paths between any 2 nodes, vertices. With cycles in the graphs, you can. That brings extra tasks and related algorithms on the plate. First one is to find shortest path from specified vertex to any other vertex in the graph. For simplicity, let's consider initial graphs with just only one connected component for this task, which means all vertices are directly or indirectly connected. Combination of all such paths can be depicted as a structure, which actually is a tree with specified vertex as a root node. Why tree? Because each shortest path considers no other alternatives, meaning no cycles. So graph could be transformed into such a tree by removing some edges which formed cycles in a graph previously. Note that number of vertices is the same before and after graph transformation into such a tree. You might be confused that our tree doesn't look like a classic tree from books and even from our previous videos. Classic view provides parent node on the top and each subtree underneath. But remember, it's just a matter of representation. It may look strange, but structure considered as a tree as long as it represents a tree by its definition. A recursive hierarchical data structure with a root node and links to one or several disjoint subtrees. Tree definition tells nothing about representation, so you can turn your edges the way you like. Main focus for our tree is which edges it contains. And we also can just make a convention which node is the overall root node for a tree, even though it's not affecting list of edges. Since our task is to find the shortest paths from specified vertex, we can select any formal root node. And term for such tree is self-explanatory: shortest path tree from specified node. An logical example here is like a preliminary preparing tree of direct-indirect routes from your home to friends' houses, to work, stores, and maybe some other geographical points. Your home is a central starting point, root node, and all prepared routes are the shortest among available alternatives. Important fact to notice: if you want to build second shortest path tree from another specified vertex in your graph, edges of these two shortest path trees can be different. There is no universal shortest path tree for a graph. It's to be prepared for specified vertex. And let me bring another totally different task. Task is to find combination of paths to connect all vertices in a graph with absolute minimum total edges weight. For simplicity, let's consider initial graph with just only one connected component for this task as well. The goal assumes here that we need to find the minimum amount of edges to connect all vertices. And not only minimum amount of edges, but to find the only one combination, total sum of edges weights, to be the smallest. Any cycles should be eliminated, because if we remove one edge from cycle, all vertices are still connected, but total sum of edges weight is minimized, which is our goal. So some edges of initial graph will go away. And again, we talk about initial graph transformation to a structure, which in fact is a tree, after removing possible cycles, with the same amount of still connected vertices as in initial graph, but with less number of edges. Such described tree has its name, minimal spanning tree. And we need to realize that it's a universal and the only one for a graph, in terms of edges related tree consists from. Actually, there is a theorem which can be proven that there is just the only one such a tree for a graph. I don't have an answer which vertex to consider as a root node for minimal spanning tree, but it doesn't matter. What really important is a combination of edges in a tree. Our MST allows to connect all vertices in a graph with the overall smallest total weights. This is the key. If your real-life task, for example, is to build cable or optical network in the neighborhood and save on materials, MST is your best friend. If you need less overall cable length in the office building to connect all computers in the network, think about MST. If you want to save on materials when building roads between several cities, plan roads with MST in mind, with its economical optimization. Please note that these two newly introduced terms, shortest path tree and minimal spanning tree, solve different tasks. They may contain different edges from the same graph. Moreover, several shortest path trees built from the different specified starting vertex of the same graph also could contain different edges. One more thing. Shortest path tree is used for the task to find shortest path from specified vertex to any other vertex in the graph. Consequent subtask here is to find shortest path from specified vertex to another vertex between two vertices only, which is already known if you have shortest path tree. You just need to point out which vertex to be the second, the target one, among the rest within a tree. Let me bring more official terms for newly introduced trees. Auxiliary term is needed. Spanning tree of undirected connected graph is a subgraph which includes all of the vertices of initial graph with minimum possible number of edges. Just note that as a tree, it's also acyclic, has no cycles, and connected. The whole tree is one connected component. Any two of its vertices still have direct or indirect path between them. Return to our two terms. Shortest path tree, rooted at certain vertex, is a spanning tree of a given undirected graph, such the path distance from specified root to any other vertex in a tree has the shortest path distance. Minimum spanning tree is a spanning tree with minimum sum of its edge weights. We were discussing terms related to structures before and after graph transformation. When it will come to an algorithm implementation, which is a process between initial and finalized structures. Such process includes visiting graph vertices using links, edges between them. And this process has its own name, graph traversal. Remember this term as well. There is another group of tasks related to, let me call it, system throughput. Let's imagine pipe with certain diameter along its entire length. The smaller a diameter, the lower amount of gas or oil per minute such pipe can deliver from source to target point. Throughput is a measured amount of something which can go through our system at a certain given time frame. And it can be used to determine overall system performance. Now imagine our system made up of several pipes consequently connected to each other, and each pipe has its own diameter. If diameters of all pipes are the same, then throughput of our whole system will be the same from end to end. But what will be overall system throughput if at least one pipe somewhere in between has a smaller diameter? You can guess, if even small part of the system has constraints, like smaller throughput, then overall system throughput will be downgraded to the throughput of its slowest part. Sometimes such situation named as a bottleneck effect, when the narrowest section of the system affects overall system throughput. In our example, we have very simple graph with just the only path between source and target points without alternatives. But systems may have alternative paths between same points, including several cycles. So you may not intuitively understand what will be overall system's throughput, which needs to be calculated. Therefore, here we have few more terms which will help to solve such throughput task. Let's look to our connected graph. Let's have assigned source vertex S and target vertex T, and some material to flow from source to target vertex. We can imagine such graph divided into two disjoint parts. Each vertex belongs to either of two parts. Note, no unattended vertex left. One part contains source vertex S, another part contains target vertex T. Such partition of a graph named ST cut. You can partition the same graph different ways with vertex S on the left and vertex T on the right, but different combinations of vertices in each disjoint part. In other words, you may have several ST cuts for a graph. Next term within throughput topic. Edge capacity is a maximum throughput assigned to a graph's edge, some number like we similarly assigned for edge weight discussed before. ST cut capacity is the sum of capacities of the edges from first part containing vertex S to the second part containing vertex T. Important thing here is, for ST cut, you may have more than one edge between both partitions, and ST cut capacity is actually tells about maximum throughput from one partition to another one, which can be reached when all edges between both partitions are loaded at a maximum of their capacity. Important, we need to keep in mind direction of our flow from S to T vertex, because sometimes graphs may be directed and have different capacity on opposite directions between two vertices. Notice here, ST cut itself has vertices in focus. How we divide initial graph into two subsets of vertices. ST cut capacity, in contrary, has edges capacities in focus. Even though our edges, imaginary pipes, may have maximum throughput reflected in capacity value assigned to an edge, actual flow of material in real life can be lower. For example, we have not enough material to load our pipes at a maximum capacity. Let's have another term, edge flow, which is assignment of a value as per current edge load. Edge flow's value has capacity constraint, which means edge flow value can be between 0, no material is flowing, and edge capacity, maximum throughput reached. In real life, most vertices considered as transit points which don't store material flowing through them. Another term, local equilibrium, explains that. Local equilibrium means incoming flow, inflow, equals to outgoing flow, outflow, for every vertex except start and target vertices S and T. Notice here, edge is in focus of edge flow, vertex is in focus of local equilibrium. We need to clarify here that every vertex may have several inflows coming from several edges, as well as may have several outflows going to another several edges. Just imagine rivers. When one river flows into another, amount of flow downstream after merging will be equal to incoming flows before merging. Another example is about a river delta, when river enters lake, sea or ocean and can be separated into several sleeves. Incoming main throughput of water will be equal to sum of outgoing throughputs of all sleeves. And there might be a mix of both examples, when we have more than one inflow and more than one outflow at a certain vertex. From edge flow, we are ready to move to ST flow term, relevant to the whole graph. ST flow includes assignment of each edge flow with capacity constraint between 0 and edge's capacity, and local equilibrium for every vertex except S and T, meaning inflow equals outflow. With these new recent terms, we'll see a couple of important problems to solve. Minimum ST cut, Mincut problem. Find the cut of a minimum capacity. Maximum ST flow, Maxflow problem. Find a flow of a maximum value. Technically, these both problems are related to each other and our bottleneck example. Remember, we discussed system made up of several pipes consequently connected to each other a minute ago. If a small part of a system has constraints, like smaller throughput, then overall system throughput will be downgraded to the throughput of its slowest part. This was a simple example with just one path and no alternatives. With this example, it's easy to find mincut. Whichever single edge on the way has the minimum capacity, because any ST cut will have just one edge in this example. Minimum flow value through the whole system will be actually limited by mincut capacity. So you can see that both problems, Mincut and Maxflow, are related to each other. With more complex graphs, we may have several alternatives, meaning we can have two or more edges between both partitions of ST cut. But similarly, playing with all potential combinations of ST cuts, you can find a cut of a minimum capacity, regardless of number of edges between ST partitions. And such a cut will represent maximum flow value system potentially can handle through, because any other ST cuts will have higher capacity than our mincut. Therefore, other alternatives to mincut cannot lower down our throughput even more. I will wrap it in a simple way as Maxflow-mincut theorem. Value of the Maxflow equals to capacity of a mincut. Mincut Maxflow approach is similar to more complex graphs with lots of vertices and edges. Let's wrap up what terms we discussed so far. Graph, undirected graph, directed graph or D-graph, edge-weighted graph with weights assigned to each edge, path, both direct and indirect, vertex degree showing how sparse or dense our graph, connected vertices, connected component, cycle, shortest path tree and minimal spanning tree to potentially transform our graph into, ST cut, graph partitioning, edge capacity, edge flow with capacity constraint, ST cut capacity, local equilibrium, ST flow, Mincut and Maxflow problems. We built minimum terms database. Before moving to the next topic about practical use cases, I would like to tell one story about preprocessing. This is about preliminary processing something for the purpose of further convenient, optimal use. For example, you can preliminary cook something. Let's say you pre-cook several pizzas with standard topping lists, put in cold for storing, and when later client orders, you just count needed types and amount of pre-cooked pizzas to be baked and delivered. This two-step process with pre-cooking and finalizing order is more convenient and faster than making every pizza from scratch for an order. First of all, the last step, finalizing order from prior pre-cooked pizzas, takes significantly smaller amount of time, sometimes even constant amount. Remember our big O notation. You also can optimize a way of preprocessing by using more optimal algorithm, by for example separately preparing and measuring all ingredients, making similar steps one after another as a conveyor, and so on. Similarly, in computer science Preprocessing refers to initial input data to produce different data for further analysis. Probably you remember from one of our previous videos what algorithms about technique named reduction used when you design algorithms. It's about a possibility to divide overall task into subtasks when possible. Once divided, we can try to find the best, for example, fastest algorithms to solve each subtask. We had reduction examples when we initially sorted mobile phone contact list in alphabetical order for further fast particular name search. Such names sorting is actually preprocessing of data for further use on a second step, name search. Preprocessing makes more sense and efficiency if it is used preliminary just once, but second, final and assumingly very fast step of further analysis is used multiple times. Now it's time to see how graph-related terms can be useful. At the very beginning of the video, we saw lots of surrounding things around us, which can be represented by graphs. And consequently, there are lots of tasks to be solved for such a representation. They are our use cases for implementing algorithms. Let's talk about them. We will start with a group of relatively similar use cases related to path, then to cycles, then move to connectivity, and finish with complex flow and capacity, from easy to more complex scenarios. There are other groups, but mentioned 4 will be enough to be covered in our add-on videos to see how graphs could be useful. Path group. First use case. Is there a path between S, source vertex, and T, target vertex? Why it may be important? Because you can solve applied tasks. Transportation problem. Can you deliver something from point S to point V or not? Communication problem. Can computer S send data to computer T through the network? Or can telephone S reach telephone T? Medical epidemiological problem. Can person T to be ill with the same disease as person S, if disease could spread between people communicating with each other directly or through other people? And lots of other tasks. Path group. Second use case. What is the shortest path between S, source vertex, and T, target vertex? While previous task was the qualitative one, we are good as long as we can find any path. This task is quantitative. We're interested in just one particular path among potentially several available. Since direction from source to target vertex is important, edge-weighted D-graph to be used. Optimal transportation problems could be in focus. To build initial route on a map, like Garmin GPS device or Google Maps do, to find shortest path from point S to point T, calculated in miles. Or build alternative rerouted path in case of main route is congested. Los Angeles traffic jams, optimal rerouting task. General urban traffic planning. Robot navigation, for example Amazon warehouse, to prepare packages with minimum robot overall distance trips. Optimal communication, network routing problem, using OSPF, BGP, RIP, special protocols to send packets from computer S to computer T at the shortest possible time, and so on. Path group, another use case. What is the list of shortest paths from vertex S to all other vertices? This is actually about building shortest path tree from vertex S, and you already know this term. Or when we may need to know the whole list of shortest paths. In practice, it may be related to communication network problem. For example, to find fewest number of hops from computer S to list of other nodes in the network. Edge weights in this case are out of scope, but number of edges, our hops, on the way is in focus. For simplicity, we can think of non-edge weighted graph or graph with all edges weights equal to 1. Or it might be expanding our optimal transportation problem previously discussed for shortest path between S and T vertices, where edge directions are important. We can have preprocessing task to build shortest path tree from vertex S to any other vertex. And then transport company with distribution warehouse center in vertex S can deliver goods to any other destination point, whichever will be chosen later from any preprocessed. So shortest path from S to V vertex is a second step after first step of preprocessing graph into shortest path tree. Moving to another group. Cycle group. First use case. Is there a cycle in the graph? Task of detecting alternative routes. Just to know that graph is not a tree, and therefore there might be alternative paths between some vertices. Now about practical tasks. Problem of preventing error when endless cycle dependencies not to travel forever looped within the same cycle. Or vice versa, problem of forcing to use cycles at your favor. Game problem. For example, when you're losing a chess game and you can find cycle of repeating moves endless way to have game draw instead of lose. In this case, board position is a vertex, legal move is an edge, so game can be looped in a cycle of the same board positions repeated one after another. Sorry if you don't know rules of chess game, just be focused on the fact that draw is better than game lose, and cycle is the key to move game from lost to a draw one. Next problem is about drawing a cyclic spanning tree by detecting and removing cycles from initial graph. For example, to build to minimum spanning tree or shortest path tree, and so on. Cycle group, another use case, Euler tour. Is there a cycle that uses each edge exactly once? This can be a practical task for a tourist to visit each road, street, bridge just once in a new city. Cycle group, another use case, Hamilton tour. Is there a cycle that uses each vertex exactly once? This is also can be a practical task for a tourist, but to visit certain places just once, regardless of roads in between. Moving to the next group, connectivity group. First use case, find all vertices connected to a given source vertex S. Vertices to be found are in the main focus of this use case. But look, additionally you will have an auxiliary outcome, set of edges connecting those vertices, directly and indirectly to vertex S. What do you think? Is it possible that you can have the same set of vertices connected to a source vertex S, but different set of connecting edges? If your answer is yes, you are totally right, because graph may have cycles and alternative paths, so the same set of vertices can be connected different way. To find an answer for the use case, kind of spanning tree will be built from the root vertex S. Spanning tree by its definition contains minimum possible number of edges from initial graph, remember that? And we want optimized algorithm with minimum steps and consequently minimum edges. As a result, there will be no cycles in our use case's auxiliary outcome, set of edges. That's exactly about building a spanning tree. During graph traversal process, which is visiting vertices and building this spanning tree, we may choose to explore graph different ways. Let's mention a couple of strategies. One of the strategy is to visit vertices in levels by level increasing distance from S. Do you remember we discussed binary tree levels on a previous add-on video, Why Algorithms? First level of a tree nodes are directly connected to the root. Second level of a tree nodes directly connected to the nodes on the first level, and so on. Similarly, in our given graph, we will visit on the first step all vertices one by one directly connected to vertex S, kind of our first level visit. On the next step, we will visit all vertices one by one directly connected to vertices visited prior on the first step. On each step, we are going one more edge further from the vertex S, ignoring any possible cycles, edges between vertices with the same distance from vertex S, and so on till last connected vertex is explored. We can, for analogical reasoning, imagine archaeologists discovering ancient city. They discovered some few thousand old city at certain starting digging point. Instead of digging in just one direction, for example to the west only, they are trying to excavate first level of adjacent land to starting point in all directions around, in hope to see that city's remains could be found there. Next day, they excavate even further, discovering day by day land at the same distance from starting point in all directions around, till ancient cities' remains can be found at each direction. Connected vertices, our excavated land, can be exhausted in certain directions, if cities' remains couldn't be found. The main idea, we slowly discovering structure at the same edge number distance in all directions which have connected vertices. This traversal strategy is ideal for minimum number of edges group of tasks, when any vertex in our build spanning tree out of initial graph can be reached with minimum number of edges from vertex S among any possible alternatives. Well-known application within this group is fewest number of hops in a communication network. Let's have a computer network diagram. In our particular network diagram, all vertices are connected to selected vertex S. But you won't reach this vertex D through any longer paths like these ones, because your spanning tree will be built level by level from vertex S. First you visit these vertices through these edges, and vertex D, which belongs to second vertices level, will be discovered on the second step. And there is no need to build any other paths to vertex D. After step 2, once it's already discovered and added to list of vertices reached from vertex S. So our increasing distance by levels strategy allows to discover the most optimal spanning tree in terms of minimum number of edges to all vertices connected to S. Alternative strategy is to explore unvisited vertices as far as you can from vertex S. We can name it deep dive maze exploration. Mazes were discussed even in ancient literature. Even though you know that there is at least one entrance and one exit, it's so easy to get lost in a maze because of complicated routes with lots of dead ends. Usually exit is not very close to an entrance. So our previous strategy to visit vertices in level by level increasing distance from S is not so effective. We will most likely spend a lot of time before reaching exit. So it's better to walk ahead as much as you can till dead end or potential exit. In real life, not to get lost, it's better to use unrolling ball of string to know return path all the way to entrance. If you reach dead end, return back till intersection and explore till another dead end in alternative path, and so on. Entrance, intersections, and exit are represented as graph vertices. That's a brief idea. Find an exit is just one subtask of maze exploration, which can be stopped as long as exit is found. But let's return to our main use case to find all vertices connected to a given source vertex S. Therefore, we don't stop after reaching certain vertex, but continue till exploring all vertices directly, indirectly connected to S, which looks like rebuilding the whole maze with all entrances, exits, and dead ends. Intuitively, you can feel that on the first step you may visit vertices connected far away from the vertex S. Totally opposite strategy from the first one, increasing distance level by level. Therefore, maze exploration strategy is not good to solve fewest number of hops in a communication network task, since you may reach actually very close neighbor vertex through the whole deep dive cycle. Now you know two mostly used strategies and corresponding types of use cases applications. Just to remind, selecting strategy has main focus on auxiliary outcome, set of edges in our build spanning tree. Additionally, on the top of all applications, final result of this use case, which is set of vertices, can be considered as preliminary preprocessing step for other connectivity and path-related cases. We'll discuss in a moment. Connectivity group. Next use case. Is there a way to connect all of the vertices in a graph? Since we already know some graph-related terms, we can ask this question differently. Can we make just one connected component involving all graph vertices? Imagine a trick to simplify algorithm. Our connected component to have own identifier, and we mark all vertices using the component ID. It's actually a key idea for an algorithm. On a previous step, we discussed use case how to find all vertices connected to a given source vertex S. We can mark all vertices directly, indirectly connected to vertex S, including S, by component ID while traversing a graph. If all vertices of a graph are marked by the same ID and no unvisited vertices left, then we can easily answer a main question of a current use case. Is there a way to connect all of the vertices in a graph? Do you agree? Connectivity cases can be used as preprocessing step for further use. If we preprocess graph to make sure all its vertices are within the same and the only one connected component with its ID, Then we can solve the very first discussed path-related use case in this video, with its transportation, communication, medical, epidemiological, and other problems. To solve use case, we need to answer a question: is there a direct or indirect path between any two vertices in a graph? Now remember idea for an algorithm to answer this question. Two vertices are connected if they have the same connected component ID after graph preprocessing. Looks simple, isn't it? Simplicity is the key. Connectivity group, another use case. Is there a way to find all connected components if more than one in a given graph? This problem is very similar to the very previous one. The only difference is you will have more than one connected component ID to mark all graph vertices, one unique ID per each connected component. It also looks like a preprocessing subtask. This subtask could also help to answer a question: is there a path between S and T vertices? The answer is, two vertices in such preprocessed graph are connected only if they belong to the same connected component and marked by the same component ID. There might be other practical tasks as well, like for example, graphical problem, to change color of the region with pixels of the same initial color. Pixels are considered as vertices and they are directly connected if they are adjacent. Therefore, the whole region consisting of adjacent pixels considered to be within the same connected component. Probably you remember some graphical applications when you have pictures region of a one color, let's say white, and you want to change white color to blue one for the whole region. You click on any pixel within this region and program applies the same blue color to all vertices, pixels of this connected component. So whole region with preliminary white color becomes region with blue color. Connectivity group, next use case. What is the best way to connect all of the vertices? The best way can be considered in terms of minimum total weight of all edges. Since we already know some terms, this task can be presented different way: how to build minimal spanning tree. While previous connectivity tasks about connected components were the qualitative ones, we are good as long as we can find connected components. This task is quantitative. We are interested in just one and the only one particular minimum spanning tree. Practical problem to solve here is expenses optimization problem. To build something with minimum amount of materials, for example, to build neighborhood fiber optic communication network with minimum overall length of optical cable. Connectivity group, another use case, B-connectivity. Is there a vertex which removal disconnects our graph? Practical system vulnerability problem, a risk of disconnecting supply channels in the absence of redundant routes. Going to the next group. Flow and capacity group. Use case, dual Mincut and Maxflow problems, which we discussed, are underneath these use cases group. Mincut, find the cut of a minimum capacity. Maxflow, find the flow of a maximum value. Practical goals, to maximize flow of supplies through existing routes. It might be supply of anything from oil, gas, till any cargo system to carry loads within specified time frame. Or maximizing information flow to certain set of people via social networks or communication networks in general. Or another vice versa goal, most effective cut of supplies or cut of communication to a people via graph's bottleneck, which is a mincut. Network reliability redundancy problem. To architect network which is able to redistribute traffic without any loss in case some routes with their max throughput could be all at fault or down. Distributed computing problem. To calculate maximum computing power of the whole system. Distributed data mining problem as just one example. And many more flow capacity use cases. We briefly touched some use cases grouped into path, cycle, connectivity, flow and capacity categories. There might be lots of other use cases, but our goal is just to share a kickstart for you to spark your interest for further study. You can see how useful practical scenarios might be. Are you interested in the effective ways to solve such practical tasks? Then let's meet in the next add-on video for why algorithms. See you there!